When the fathers of quantum theory formulated their ideas, they had no idea that both the proton and the neutron have their own magnetic moment. Unfortunately, they didn't have all the necessary pieces of the puzzle to build their theory. And so it came to pass that this theory only works with electrostatic energy and completely neglects magnetic energy. Is it possible that the later demonstration of such important properties as the magnetic moments of elementary particles would have had no influence on the shape of quantum mechanics? Without this knowledge, a model of the hydrogen atom based only on electrostatic and centrifugal forces was created. Although the moving charge created an orbital magnetic moment called the Bohr magneton, this magnetic field was ignored because it had nothing to interact with. So what would a model of a hydrogen atom with a proton that has a magnetic moment look like? How would the magnetic moment of a proton interact with the orbital magnetic moment of the moving charge of an electron? How would the magnetic moment of a proton interact with the intrinsic magnetic moment of an electron, which was experimentally proven and measured only in 1947? Since the magnetic moment has been experimentally proven and measured for all elementary particles, let's see what the magnetic moment tells us about elementary particles. We know from physics that the magnetic moment of a planar conducting loop with an area S, flowing with a constant electric current I, is equal to the product of the current and the surface and is oriented in the direction of the normal of the surface according to Ampere's right-hand rule. Thus, if elementary particles, a proton, a neutron and an electron, have an experimentally measured magnetic moment, then we can hypothesize that all these elementary particles have the same structure similar to a current loop, where the current is created by the movement of the charge along the ring or toroid. For the proton and neutron, the ring theory works with the hypothesis that three quark particles always define a plane. If there is an exchange of energy between these particles, for example by the movement of charges in one direction, then we can also associate this process with an electric current in a closed current loop, and we can apply the known physical laws of electromagnetism to it. What about the electron? Can we assume that we will encounter a similar structure to the proton and neutron in the electron? The structure of the electron has not been experimentally proven and appears to be a material point. We know that it is a carrier of electric charge, it has a wave nature, it has a magnetic moment, and its energy is quantized. Can we create a form of electron that would meet these properties? In terms of physical size, the electron is considered a point particle with zero physical radius within current measurements and theoretical models. If we were to use the term mass center instead of the term mass point, it could lead us to imagine a ring composed of smaller substructures, all of whose mass is concentrated at this point. If we start from the history of understanding the structure of matter, we can see that the dimensions of the size of elementary particles have been constantly decreasing. At present, we are able to use accelerators to investigate particles with a size of approximately 10 to 18 meters, which we say are probably no longer divisible. However, the theory presents us with the possibility of the existence of something much smaller with the size of the Planck length, which is referred to as the physical constant of length, and is approximately equal to 1.6 times 10⁻35 meters. This difference in size by another 17 orders of magnitude is approximately the difference between a human and a quark, between which there are several levels of structures and substructures of matter. And so it is a completely legitimate question whether the elementary particles known to us so far are not also made up of some substructures that we do not yet know about and that we are not able to discover with the current possibilities of technology and our knowledge. One of the theoretical possibilities of investigating the behavior of these substructures is the modeling of elementary particles according to the ring theory. Elementary particle models are fractal made up of multi-level ring structures that are bound to each other by electromagnetic forces. If we admit the possibility of the existence of these substructures, then we can use the same structural basis for models of the photon, electron, positron, quark, neutron and proton. Ring theory offers a model of the electron as a dynamic, toroidal-shaped particle, which is made up of multi-scale composite ring substructures. These substructures are bound to each other by an electromagnetic field. The model of the electron can be modeled as a closed structure composed of oscillating ring substructures. The oscillation of the substructures is formed by standing oscillations with the same amplitude, but with a shifted phase of the individual substructures. The phase shift of the oscillating substructures creates a progressive wave. This basic model structure of the electron is a half wave. The substructures of the electron model do not rotate, but oscillate. A traveling electromagnetic wave, which originates on phase-shifted oscillating substructures, is able to transmit electrical power at its peak, which we call electric charge. According to the direction of rotation of the substructures and the direction of the phase shift, a positive or negative charge is defined. This structure is both a wave and a particle. Such a structure allows the proposed model of the electron to react by changing the radius, to a change in the binding energy, or to a change in excitatory energy. Such an electron model meets all the requirements we have set for the electron model. Ring theory assumes that the electron is actually a closed photon. Therefore, the electron at the ground level is made up of a closed half-wave. Therefore, when two photons collide, an electron and a positron can be formed with opposite rotation. At the second energy level, the electron is made up of two half-waves. At the third level, it is made up of three half-waves, and so on. The magnetic moment vector in a multi-level structure is defined by the direction of rotation of the substructures, and the direction of the charge movement along the outer circumference. For an electron with a negative charge, the direction of the magnetic moment vector is determined according to Ampere's right-hand rule. For a positive charge, the left-hand rule applies. The direction of the magnetic moment for the proton and neutron is the same as the rule for positron. In quantum mechanics, the existence of a physical magnetic moment vector has been replaced by a mathematically defined spin. Similarly to the ring structure of the electron model, the photon model can be modeled as an open ring structure composed of oscillating ring substructures. The oscillation of the substructures creates a standing oscillation with the same amplitude but different phase. The phase shift of the oscillating substructures creates a progressive wave with free ends, on which waves with the same phase are reflected. The structure of the photon modeled in this way is a half-wave. Gradual waves transmit energy. The energy oscillates from front to back and at the same time rotates around the longitudinal axis of the photon. For a photon modeled in this way, we can determine the direction of the photon's motion, which is identical to the direction of the magnetic moment, and the plane of circular polarization, which is perpendicular to the direction of the photon's motion. It has been proven that the intensity of the electric and magnetic fields change simultaneously, and therefore the coordinates of the points in space where the intensity of the field changes are functions of time. The similarity of the structures of the photon and the electron and their entanglement of wavelengths allows us to quantify the size of the electron radius, which is further necessary to calculate the bond length and binding energy between atoms in molecules. Because the ionization energy of photons varies from atom to atom, the magnitude of the electron radii at the fundamental level and at other energy levels are also different. The entanglement of photons with electrons will be shown by determining the size of the radius of the electron model of a hydrogen atom at the fundamental level. The magnitude of the radius of the hydrogen atom electron model at the ground energy level is based on the wavelength of the photons of the terms of the spectral lines of the Lyman, Balmer and Paschen series. The radius of the electron of the hydrogen atom at the ground level is calculated by the formula term times the constant alpha divided by 4 times 2 pi times n squared, where n is the energy level of the individual series of spectral lines. After substituting the values, we get the quantified size of the radius of the hydrogen electron model R at the first energy level of 2.65 times 10 to the minus 11th meter. The size of the electron radius calculated in this way corresponds to the experimentally measured value. Since the energy around the circumference of the electron moves 137 times slower than the speed of light, then the recalculated wavelength of the electron lambda is 22/808 nanometers. The internal energy of the electron, including the energy of the substructures, is 54/394 electron volts. A quarter of this energy is the same as the binding and ionization energy of the electron of the hydrogen atom at the ground level. If we replace the spherical model of the proton with the ring model, and place it in the center of the mass of the electron model with a multi-level ring structure, along the circumference of which the electric charge moves, then significant changes will occur in the relationships between the proton and the electron in the hydrogen atom model. From this model, it can be seen that the magnetic moment of the electron is identical to the orbital magnetic moment and is not related to the angular momentum of the electron. The difference in electrostatic interaction between point and ring electrons can be shown in the following graph. In the Bohr model, as the distance between the proton and the electron decreases, the magnitude of the electrostatic force increases exponentially inversely proportional to infinity according to Coulomb's law. On the other hand, in the ring model, as the distances between the proton and the electron on the common axis decrease, the electrostatic force in the ring axis, after the initial increase, decreases to zero. The magnitude of the electrostatic force is affected by the magnitude of the electron's radius. To explain the magnetic interaction between a proton and an electron, we can associate a proton with a current loop based on the magnetic moment. Then, by applying Biot's, Savart's law, we can determine the magnitude of magnetic induction at the point P, located outside the axis of the ring. If this point is located on the ring of the electron model, then the inhomogeneous magnetic field of the proton will exert a force on the electron current loop. The magnitude of this magnetic force in the axis of both rings can be expressed using the modified Biot-Savart law. If the vectors of their magnetic moments are antiparallel, then the force between them will be repulsive. Using the laws of physics for the attractive electrostatic and repulsive magnetic force between the ring models of the proton and the electron, we can create a model of the hydrogen atom based on the equilibrium of electromagnetic forces. The proton and electron are kept on a common axis at a distance d in dynamic equilibrium by the electric force of attraction and the magnetic repulsive force. The electric force in the ring axis is calculated using Coulomb's law and the magnetic force according to Biot's, Savart's law. In these equations, we express the hypotenuse r and the sine and cosine functions in terms of the values of r and d. Since the movement of the charge is not linked to the rotation of its structure in the ring structure of the electron, there is no need to take into account any kinetic energy or mass of the electron. To calculate these forces, we need to know the radius of the electron r. As we have already shown, the size of the radius of the model of the hydrogen atom electron at the fundamental energy level is based on the terms of the individual series of spectral lines. To calculate the magnetic force, it is also necessary to quantify the value of the electron current. When we plot the values for the electrostatic and magnetic force as a function of distance on the graph, we get two curves that intersect at one point. This point indicates the distance at which the equilibrium between the electrostatic force of attraction and the magnetic repulsive force between the proton and the electron on the common axis occurs. From the modified equations for the equilibrium state between electric and magnetic force, we get the formula for calculating the distance d on the common axis. After substituting the constants and the previously calculated values, we get the value of the distance between the proton and the electron at the basic energy level of the hydrogen atom in the value of 2 whole 34 times 10 to the minus 11 meters. This value corresponds to experimentally measured values of the size of the hydrogen atom. The proton and electron in the hydrogen atom model are in dynamic equilibrium of electrostatic and magnetic forces. In the graphical representation of the equations for electric and magnetic force on a common axis, we can see that at a distance greater than the equilibrium position, the attractive electric force prevails, while at a distance less than the equilibrium position, the repulsive magnetic force prevails, which returns the electron to the equilibrium position. This property of electromagnetic forces allows dynamic equilibrium to be maintained around the distance d. From the equations for the calculation of electromagnetic forces, we can express the equations for the calculation of electric and magnetic energy in the x-axis. From the graphs of these equations, it is clear that there is no balance between energies at the distance of the balance of forces, but magnetic energy has a greater value than electrical energy. The difference between the energy of the electric field and the energy of the magnetic field in the x-axis at the point of equilibrium of forces gives the value of the energy that we have to supply to this system to separate the proton from the electron. This value is called binding energy. In the case of a hydrogen atom at the fundamental energy level, the bonding energy is equal to the ionization energy. The importance of the wavelength of spectral lines is not only in determining the excitation energy of the photon. From the spectral lines, we can also obtain information about the radius of the electron and its circumference, but also about the proper size of the photon and the distance between the proton and the electron. The table shows values from the database of photon wavelength spectra during the transition between adjacent energy levels of a hydrogen atom. From these wavelengths of the photons, the electron radii at the individual levels n are calculated. The following columns show the calculated values of the differences in radii between the individual levels, the circumference of the electron and its increments, the energy of the photons and the levitation distance between the proton and the electron on the common axis. The wavelength of the photons between the n and n+1 levels increases exponentially by the principal quantum number n when the electron of the hydrogen atom is excited by 1 degree at a time. The radius of the electron increases linearly with increasing principal quantum number n when the electron of the hydrogen atom is excited by 1 degree at a time. Since both the electron and the photon are made up of dynamically connected substructures, the beginning of the table and graph shows a strong deformation influence of the components of the EMG force vectors of the proton that are directed to the center of the electron. The increment of the electron circumference is limited to 33.27. Thus, we can agree with de Broglie's hypothesis that when an electron is excited to the nth higher energy level, the fundamental wavelength of the electron increases n-fold. However, this magnitude is significantly affected by the electric and magnetic force of the proton at the lowest values of the quantum number n of the electron, as documented by the magnitude of the photon wavelengths from the table and the spectra database. We can hypothesize that with a constant increase in the electron circuit, there is a constant increase in the number of substructures in the electron circuit. This would mean that even the excitation photon between the levels has the same number of substructures even at different photon wavelengths. The consequence of this hypothesis would be an increase in the mass of the electron at individual levels to the final experimentally determined mass of the free electron. From the graph of the distances of the electron from the proton of the hydrogen atom model, it is clear that with increasing quantum number and increasing radius of the electron model, the distance increases up to the 8th energy level. As the radius of the electron increases, the magnetic repulsive force decreases faster than the electric force of attraction, and the distance of the electron from the proton on the common axis decreases until the planes of their rings are aligned. This condition allows the proton and electron to reorient their magnetic moment vectors relative to each other while using the minimum energy of the photon in the hydrogen spectrum known as the hydrogen line at a wavelength of 21 whole 1 centimeter. The hydrogen atom model is found in two modifications in terms of the magnetic moments of the proton and the electron. The deuterium atom can be considered an isotope of a hydrogen atom, enriched in the nucleus by one neutron. Since the ionization energy of deuterium is almost identical to that of a hydrogen atom, we can also use the same electron radius as a hydrogen atom. In the deuteron model, the addition of a neutron does not change the magnitude of the electric force, but by combining the magnetic moments of a proton and a neutron, the magnitude of the magnetic force is doubled. After analyzing the equation, the distance of the electron from the proton and thus the atomic radius of deuterium is 4.2 times 10 to the minus 11 meters for the dynamic equilibrium. To build a model of the tritium atom, we will use the same approach as for the deuterium model with the addition of another neutron. The magnetic force will be 3 times greater than that of a hydrogen atom. The resulting distance for the equilibrium state and the radius of the tritium atom model is 5.5 times 10 to the minus 11 meters. Now we will look at how the magnetic moments of protons and neutrons can affect the structure of atomic nuclei. It was experimentally proven that both proton and neutron have their own magnetic moment and their value is measured. Let us recall that the magnetic surface, ampere, moment is a vector physical quantity of a planar conducting loop with an area S flowing with a constant electric current I and is equal to the product of the area and current and oriented in the direction of the normal of the surface according to Ampere's right-hand rule. The magnetic fields of proton and neutron rings interact with each other in a similar way to the magnetic fields of ring permanent magnets. Rings of magnets with parallel magnetic moments on a common axis attract each other in the same way as rings and anti-parallel magnetic moments outside the common axis. A proton and a neutron located on a common axis with parallel magnetic moments attract each other. A proton and a neutron with anti-parallel magnetic moments placed next to each other attract. The possibility of assembling models of protons and neutrons into a model of atomic nuclear structures was described in 2010 by Professor Pavel Osmera. Models of atomic nuclei can be composed using 4 basic structures, composed of 2, 3, 4 and 5 pairs of protons and neutrons. In the following text, we call them globules. A model of an atomic nucleus can be constructed from ring protons and neutrons using the following rules. A maximum of 2 protons with a parallel magnetic moment can be connected on a common axis. A proton and a neutron with a parallel magnetic moment can be connected on a common axis. 2 protons with different axes can be connected through a neutron. 1 or 2 neutrons can be inserted between 2 parallel protons. It turns out that it is possible to combine these four basic rules to create a highly variable to arbitrary structure of the nuclei of individual atoms known from the periodic table of elements. With the help of structural transformations, a number of phenomena can be explained, using pictorial representations and images. Ring protons and neutrons are bound to each other by a magnetic field, which is created by the rotation of the electric charges of quarks inside their rings. Because the proton and neutron have magnetic moments in the globule opposite to each other, their magnetic fields superimpose each other at the point of approach and as a result attract each other. However, due to the chosen concept of the model of the ring structure of nuclei, these fields interact with each other only in a quarter of their circumference. When the ring planes are clamped at an angle of 120 degrees at the point of contact, both magnetic fields are perpendicular to each other, and after reaching 45 degrees, their force effects decrease strongly, to zero. That is why we say that nuclear forces are short range. At this point, the ring theory and model correspond to the experiments carried out so far, and therefore we can assume that there is no special, strong nuclear force, but only a strong standard magnetic force in the structure of the proton and neutron rings. According to the ring theory, the most important thing for the properties of elements is the structure of their nuclei, which determines the position and properties of electrons bound to protons in the nucleus of an atom. The structure of the nuclei is formed in such a way that one electron is bound to each proton. For example, the nucleus structure model of a carbon atom consists of two globules, which are made up of 3 protons and 3 neutrons. They are bound to each other via a proton bridge and are held together by the electromagnetic field of both protons. Nucleons in an atomic nucleus assembled according to the ring theory model have their magnetic moment. By rotating the charges of quarks, they are bound to neighboring nucleons by means of magnetic field components and thus form deterministically and explicitly defined bonds. They can be described at any point in time as a familiar system from an automobile transmission. The planes of these globules are perpendicular to each other. One of the most important elements of the structure of the nucleus model is the distribution and orientation of the magnetic moments of the proton rings in neighboring globules. In one globule, the magnetic moment vectors of protons point inward into the globule, and in the other globule, the magnetic moment vectors of protons point outward from the globule. Such a structure of the nucleus globules affects the orientation of the magnetic moments of the electrons, which are bound to the individual protons of the nucleus. Electrons always have an anti-parallel direction of their magnetic moment vectors with respect to the magnetic torque vectors of the driving protons. Therefore, each of the bonding electrons of both 2p and 2s has opposite direction of the magnetic moment vector with respect to the nucleus of the atom. Such an arrangement of electrons allows carbon atoms to form different kinds of bonds with other atoms. To properly understand bonds, it should be emphasized that an electron has only one type of magnetic moment, unlike mathematically defined spins. Its dual form is given only by its orientation towards the nucleus of the atom. If we move an electron from the upper globule to the lower globule, its properties do not change at all. Only the direction of its magnetic moment vector changes from the out type to the in type relative to the nucleus of the atom. It always has an anti-parallel direction to the magnetic moment vectors of its driving protons. The numbers of neutrons in atoms do not always coincide with the numbers of protons. These neutrons, additionally, strengthen the bond between the globules, but they can also reverse the magnetic moment of neighboring globules, which is needed for interaction with bound electrons. Over the last 100 years, countless models of atomic nuclei have been created. 37 models of nuclei were shown in N.D. Cook's work from 2010 alone, which, however, represented the nucleus of atoms only as a carrier of positive charge. Ring theory is a model of atomic nuclei based on the toroidal structure of protons and neutrons and their mutual coupling by electromagnetic field forces. With the help of these structures, it is possible to assemble the nuclei of all elements, to explain the importance of the structure of the nucleus for the formation and function of the electron shell, and to show the necessity of neutrons in the construction of the nuclear structure. This model is completely consistent with the entire ring theory. Using the ring theory, it is easy to explain the bond between atoms. One of the basic bonds is the covalent bond. For example, imagine a carbon atom that has a certain radius and its valence electron has binding energy that is equal to the ionization energy. If another carbon atom appears nearby, then under the right circumstances they both want to be connected by their valence electrons, However, in order for the electromagnetic forces to remain in dynamic equilibrium, the atoms must leave the close distance of their atomic radii and move away to a distance that suits the balance of the electromagnetic forces that hold this bond together. At this distance, however, their bond has an energy that is less than the original atoms had together in close contact. The difference between this bond energy and the sum of the bond energies of the original atoms is called the binding energy. The greater the energy that is released when a bond is formed, the greater its value, the more tightly the atoms are bound to each other. Thus, a covalent bond is a force interaction between atoms of either the same or different elements. It is characterized by sharing one or more pairs of electrons between two elements, bond length, and binding energy. For a covalent bond to form, it is a necessary condition that the magnetic moment vectors of the shared electrons are parallel to the same direction of charge rotation. In this case, the magnetic field created by the rotation of charges will bind both rings of electrons to both protons on a common axis. This condition allows both electrons to interact with both the electric and magnetic forces of both protons of the nucleus of both bonded atoms. Because the charges of the electron rings are located on opposite sides of the rings, they do not exert a repulsive electrostatic force on each other in the ring axis. The two bonded atoms must find a bond length sufficient to ensure a dynamic balance of the attractive electrostatic and repulsive magnetic forces between the electrons and protons, and the repulsive electrostatic force between the positive protons of the two atoms. Example of a model of a simple covalent bond between carbon atoms in a model of an ethane molecule. The bond energy between two carbon atoms is calculated as the difference between the sum of the energies of two separate carbon atoms and the bond energy between the carbon atoms. First, we quantify the length of the bond based on the equilibrium state of forces, and then we can quantify the bond energy between the carbon atoms. The binding energy that is released when the bond is formed is equal to the difference between the bond energies of the separate carbon atoms and the bond energy of their connection. The calculated binding energy corresponds to the experimentally measured value. Example of a model of a double covalent bond between carbon atoms in a model of an ethylene molecule. Example of a model of a simple covalent bond between carbon atoms in a model of an ethene molecule. The entanglement of ring structures of elementary particles and the use of their magnetic moments allows us to create a simple model of atoms and molecules. Using the basic physical laws of electromagnetism, we can deterministically quantify the lengths of bonds and binding energies between atoms in molecules deterministically with a relatively simple mathematical apparatus, in accordance with experiments. Ring theory shows a different view of the structure of matter than quantum mechanics. However, if the equations given correspond to observations, and the results coincide with experiments, then it is worth considering this model of the structure of matter as possible. Thank you for your attention and open mind. For more information, visit the www.ringtheory.eu website.